Hello and welcome to my demonstration for the conservation of energy along with a few other rules in physics. I made a roller coaster. I have just pulled up some meters so you guys can see what's going on. I recommend keeping your eye on these meters throughout the ride. I'll explain after, but just know to keep your eye on the speed, vertical, horizontal, and acceleration g-forces. For those of you who don't know, g-force is a measure of acceleration relative to the acceleration of gravity. Skip the lift hill. Alright, so we've just reached the top of the lift hill. We're about 70 meters up, so there's a ton of gravitational potential energy, which will be converted into kinetic energy after this drop. Now we're going into a floater airtime hill, which should make you feel weightless / free falling. And now we're going to slam into a brake arm, which should make you fly forward in your seat because of inertia. Skip this part. Now we're about to enter a launch, which should pull you back in your seat again because of inertia, because you're accelerating. Now we're going to go through a corkscrew, which should glue you into your seat. And a 0G roll, which should throw you out of your seat. Now we're going to go into an unbanked turn, which should throw you into the side of your seat because of centrifugal force. Now we're going to go through a banked turn, which converts that force into vertical force. As you can see there, you'll feel like you're pinned into your seat. And now we've hit another brake run again, throw you forward because of inertia. And I will skip. So now we've reached the top of the lift hill. Again, same height as last time. The drop's going to be the exact same height, except this drop is way different. It's way less steep than the first one. So we'll see what the forces look like here. So keep your eye on the forces, the g-forces, sorry, and total speed. And we will analyze after. Reach the bottom of the drop, another banked turn, so you'll feel pinned into your seat. And this is an ejector airtime hill where you'll feel like you've just been shot out of your seat. And then finally another brake run, which is again inertia. Alright, welcome to part 2 of my demonstration. So this is going to be showing the behind the scenes of my simulation and just basically how it works. So this is my roller coaster editor, and I will be using the speed and g-force combs to show basically what's going on here. So roller coasters, if you didn't already know, there's no motor inside of any sort of roller coaster train. They are powered completely by conservation of energy. There's usually one element at the start of the ride. In this case, there's more because I wanted to showcase different ways to start a ride. But for typical rides, there's usually one element at the start of the ride, typically a big drop, and it just uses that energy throughout the ride. This is why the first drop on a ride is usually the tallest, because there's no motor inside the trains. So if you make airtime hills that precede drops taller than the drops, your ride will not make it over the hill because of conservation of energy. You're not going to gain any more energy after the drop. So, and friction is constantly eating away at your speed / energy. So you'll never be able to go over a hill taller than the first drop, because energy in is energy out, and roller coasters are basically powered by conservation of energy. So for the first element of my ride, I have this lift hill that brings you up to a height of 70 meters to put you into this drop. So I'll show the calculations in a separate document just because it's easier in terms of time, but I will explain what's going on here. So at the top we have a speed of around, if you look in the bottom left, when I hover over the combs, it'll show you data about it. So you have a speed of around 8 kilometers an hour. So we know there's some kinetic energy. Obviously we're 70 meters up, so there's a lot of gravitational potential energy, which the point of the drop is to then convert it into kinetic energy. And we drop to about 10 meters above ground, and our speed becomes 120 kilometers an hour. So what's going on here, basically? So at the top, like I said, energy in equals energy out. We have a lot of potential energy. We have some kinetic energy, just a teeny tiny bit. And at the bottom, we have a ton of kinetic energy, still a little bit of potential energy because we're off the ground. And we have some thermal energy that ate away at our speed while we went down this hill. So yeah, energy in equals energy out. You'll take this energy up here, calculate the kinetic energy here and this potential energy, and then the difference is the friction, the thermal energy. Then you go through this floater airtime hill, which how floater airtime hills work is so in terms of conservation energy, it's basically the same thing we just looked at. There's more gravitational energy here. You can't make them taller than the drop because, like I said, you won't be able to make it over. But now I'm going to switch to the G-force comb and we can make some interesting observations. So if I go to G-force comb and I observe the top, look at the bottom, you'll see very close to 0 vertical G's, which means that you will feel like there is no gravity, just 0 gravity experience. And that's why it's called a floater airtime hill. It feels like you're flying and just very graceful, very easy. You don't feel like you're being shot out of your seat. You just feel like you're weightless. So how does this actually work? Well, as you can see, this looks like a parabola, and that's because hills like these are modeled after projectile motion. As we learned, projectile motion is parabolic, and so this hill is modeled after the shape that the ride would take if it just vanished from the track, basically, and flew off. That's how you make hills like this, because it's meant to simulate that feeling of just free fall. So then I'm going to switch back to the speed comb as we go into the brake run. As you can see, we lose a lot of speed here, and so how this works is these brakes are friction brakes, so they basically just convert this kinetic energy into thermal energy. Then we hit a launch, which uses wheels to push the ride forward. Again, just a means of generating that initial bit of energy that we will conserve through the following elements. This launch brings us up to around 106 kilometers an hour. Now we enter a corkscrew, which is a type of inversion. This will make you feel glued to your seat because, as you can see up here, the G-force comb shows you're feeling 3 vertical G's, which means you'll feel around 3 times your weight. So you'll feel pinned to your seat. You may think, well, you're upside down, so why would you feel that way? And the force is pointing outward, it's pointing up. But you have to remember, it's all relative. If you're upside down, then up feels like down to you. So you feel like you're being pushed down. You feel like you weigh more, not that you weigh lighter. So yeah, you'll feel like you're pinned into your seat throughout this element. It's a very high G-force element. And then in complete contrast, we have a 0 G roll, which is a similar thing. It's kind of an airtime hill, but you invert at the top. And so at this one, as you can see, we were feeling some, we're feeling negative 0.33 vertical G's, which is, as you can tell, it's less than 0. So you're not just going to feel like you're floating. You're going to feel like you're being shot out of your seat, which I'll get back to later. But that's just another type of element. Now we hit this unbanked turn, and this is just a very important thing because, as you can see, this G-force comb is pointing out. It's going all yellow and it's pointing out, which means there's a little bit much of, not like too much, but there's a good amount of lateral G's. And lateral G's, they aren't terrible, but they're very uncomfortable. You're going to be slamming into the side of the ride at this point. You're feeling, I think this is 1. Yeah, it's around 1 lateral G. You're going to be slamming into the side of the ride. And this is caused probably by centrifugal force. So we obviously don't want that. And you've probably never felt like that on a ride before unless it was one of those wild mouse rides like the Fly at Canada's Wonderland. So how we do this is we bank the turn. And so what banking the turn does is it turns that force that originally was pushing you into the side into a force that pins you into your seat. And so how we do this is we just think about, again, it's all about how relative stuff is to each other. So the force isn't any different, but it's pushing you towards the side. So if you bank yourself on your side, then if it's pushing you into the side, that's now become the bottom. So instead of pushing you into the side and making you feel like you're getting pushed outward, it's making you get pinned into your seat instead. So now we can see there's almost no lateral G's and there's a little bit more vertical G-force than before. So it's converted it into vertical G-force. Again, another brake run, which does the same thing as before. And this is another lift hill. It's way steeper, so you'll feel nearly weightless on this one. I can just get it to show up. And this is a interesting drop. I made it way less steep just to show that steepness in the drop plays an effect because of friction, because you're spending way longer on this drop, so you're going to get way more friction on the end speed. It's the exact same height as before and the exact same end height, but this time we're only going 112 kilometers an hour. Also, in terms of forces on the drop, the first drop is going to make you feel thrown out of your seat, as you saw on the ride, whereas this drop is really not going to make you feel too much of anything. Again, another banked turn, and then the last element, an ejector airtime hill, which is similar to a floater airtime hill, except if you see this G-force comb, it's shooting you out of your seat. This is negative 0.42 vertical G's, which is less than 0, so you're going to feel like you're being shot out of your seat. It's not a very natural sensation. That's why it's called ejector. You're being shot out of your seat. And the way you achieve this is you take that parabola and you make it unnatural. So you either make it tighter or you make it shorter, just something like that. It depends on the situation. But as you can see, this one's a lot different looking than that. It's similar, but it's a lot shorter in this case and a little tighter. So you're going to feel like you're being shot out of your seat, and then another brake run, and then that's it.